Hello again, and welcome back to the afternoon session. And it's a pleasure to welcome Daniel Grumiller from the Institute for Theoretical Physics, Vienna, who is going to tell us about black holes, BMS 2. Okay, Daniel, over to you.
Yeah, thanks, Suresh and Gabriel for hosting this and for letting me be part of this. I wish, of course, we were in Lisbon, but it's still good to see you guys online. So I want to talk about BMS 2. I included as a subtitle most of the keywords of the conference, only BPS is missing. And that's because I'm not going to talk about supersymmetry. Does it work? Can you hear me?
Yes, we can hear you. Yes.
Good. Because sometimes the window seems a bit frozen, but okay. Yeah, so the only super that appears in my talk is going to be in the context of rotations and translations, but there's no supersymmetry in my talk. And this is work done in collaboration with two former postdocs at TU Wien, with Hamid Afshar and Hernan Gonzalez, and with a long-term visitor in Vienna, Dima Vasiljevic. So here's an outline of what I'm going to talk about. I'll give a brief motivation of why we wanted to study BMS2. Then I'll define for you what we mean by BMS2. So I'm going to focus first on the kinematics. So I'll define for you the class of metrics and fall-off conditions that we're interested in, and tell you how the corresponding asymptotic symmetry algebra looks like. And then we go over to dynamics. So we look for a specific gravity model that has metrics with this fall-off behavior solutions, and also has a centrally extended version of these BMS2 symmetries as asymptotic symmetries. And then I show how this model is related to SYK. What I mean here is by the gravity dual of it, so by the to the Chekhiv-Teitelbaum model. And in particular, we're going to show how you can derive our model as a certain singular limit of a complex SYK model. And then I'll conclude with a very brief outlook. Okay, so before giving you the motivation, let's start with a definition that is important for this talk, namely asymptotic symmetries. So just that we're on the same page. So asymptotic symmetries consist of all boundary condition preserving transformations modulo proper gauge transformations. So these are those would-be gauge transformations that cease to be gauge transformations at the boundary. So they are non-proper gauge transformations. And those asymptotic symmetries are important in various contexts. So in ADS-CFT, a basic ingredient of many of the ADS-CFT tests is based on symmetries. And the symmetries on the gravity side are just determined by the asymptotic symmetries, and they correspond to conformal symmetries on the CFT side. So this asymptotic symmetries in the ADS-CFT context, they capture universal UV features of quantum field theories, namely the conformal symmetries. And the seminal Brown-Renaud analysis from the mid-80s was, at least in retrospect, an important precursor for ADS3 CFT2. So one way to phrase Brown-Renaud's results is that they showed that if Einstein gravity in 3 dimensions exists as a quantum theory, then it must be dual to a 2-dimensional conformal field theory, in the sense that the physical Hilbert space must fall into representations of 2 copies of the Virasoro algebra. Okay, so besides ADS-CFT, asymptotic symmetries feature essentially in any type of spacetimes, in particular in asymptotically flat spacetimes, and this is where asymptotic symmetries were first discovered. So again, asymptotic symmetries are a basic ingredient for flat space holography tests based on symmetries. And in the past decade, there was a lot of progress on this. So there were discoveries of Cardi type of formulas in flat space holography, of entanglement entropy, of correlation functions. And these observables are largely determined by the symmetries. So therefore, the symmetries play an important role in these tests. In flat space, the asymptotic symmetries capture universal infrared features of the quantum field theory in the bulk. So this is part of the famous infrared triangle. So the watered entities correspond to soft theorems. The watered entities related to these asymptotic symmetries in asymptotically flat space. And similarly to Brown-Noe being the precursor for ADS3, CFT2, the Barnich-Compare analysis of asymptotically flat space Einstein gravity in 3 dimensions was an important precursor for flat space 3 contracted conformal field theory correspondences that were studied since a decade. And we can even try to go beyond this. So many of us believe that the holographic principle is a generic feature of quantum gravity and not just specific to ADS-CFT. But we're not completely sure about it, so we lack, examples. So, is there asymptotic holography beyond ADS-CFT? Is there something that we may call near horizon holography? So, can you do the same thing that you do in the asymptotic region? So, you impose some asymptotic boundary conditions, determine some symmetries, and constrain in this way the dual field theory. Can you do the same thing near the horizon? Either way, asymptotic symmetry is an important input for the structure of the dual quantum field theory in a holographic context, and that's why there's so much focus on them. Now let's focus in the rest of the talk on asymptotically flat space, and in this case, the asymptotic symmetries are so-called BMS symmetries. Here's a brief history. Until the 60s, I guess it was a sort of consensus that general relativity in the limit of low curvature should coincide with special relativity. It seemed at least natural. So in particular, you would expect that in the limit of low curvature, you should get essentially Poincaré asymptotic symmetries, because those are the symmetries of Minkowski space. But as was famously shown in '62 by Bondi, van der Burg, Metzner, and Sachs, whose acronym now reads BMS, the answer is no. You get not Poincaré, you get much more than Poincaré. You get an infinite extension of Poincaré by super translations. So instead of having ordinary translation generators, P, you have angular dependent translation generators. So you have infinitely many of them, and they're called super translations. So X here refers to angular coordinates. You can think of X as the usual theta phi coordinates of the two-sphere, for instance. Here is an extended version of the BMS4 algebra, extended in the sense that we don't just have Lorentz symmetries and super translations, but we have the full diff S2 or some restriction thereof. So sometimes these JA are referred to as super rotations. So JA are the super rotations and P are the super translations. And this is the usual diff S2 algebra. This is the mixed Poisson bracket between super rotations and super translations. And the parameter S denotes the spin of the super translation. So in the original BMS4, S was equal to 1. And those commute with each other. So that's, in essence, the definition of a translation generator. They commute with all other translation generators. Okay, and BMS found this algebra, or a restricted version of that algebra, as asymptotic symmetries of 4-dimensional Einstein gravity with asymptotically flat boundary conditions. And let me, put this as an aside, but I think it's an interesting aside. You find the same symmetry algebra as near horizon symmetries in any dimension big or equal to 3. And this was shown first by Laura Donnet and collaborators about 5 years ago. So they found this algebra for the case S equal to 0, so scalar super translations. And last year, together with postdoc here in Vienna, with Celine Zwickel and collaborators, we found that you can actually generalize the arbitrary spin. So this may have been expected on general grounds, but because the asymptotic boundary in flat space is a null hypersurface, for instance, called plus, and the horizon is also null hypersurface. So you may have guessed that you get the same symmetries near the horizon as at infinity, but well, it was not completely obvious, of course. Anyway, in the rest of my talk, I'm going to focus on asymptotic symmetries, so I'm not going to talk about near horizon symmetries anymore. Let's go down further in dimensions. So let's move to BMS 3. So about 8 years ago, Glenn, Andy and Hernan showed that you can get BMS 3 from two-dimensional CFT by contraction. So how does this work? Well, the algebra that generates the CFT2 symmetries consists of two copies of the Virasoro algebra. I denote the Virasoro basis by this calligraphic L and L bar, n is some integer. And then I do a change of basis. So the Ln is just the difference between the Virasoro generators, where I also have a minus sign in the second index here. And the mn's are some rescaled differently in the combination of these Virasoro generators. And so for any finite value of L, this is just a weird change of basis. But if you take the limit L to infinity, then you get an Inouye-Wigner contraction and you get a different algebra. So in this new basis, the Virasoro algebra looks as follows. So now I wrote commutators instead of Poisson brackets. So the first line looks just like an ordinary Virasoro algebra, or it is a Virasoro subalgebra, with a central charge that is the difference of the original central charges. That's because of this minus sign here. The commutator between L and M, so between the super rotations, if you want, and the super translations, looks on the right-hand side like a Virasoro algebra with a mixed central charge that is the rescaled sum of the original central charges. And if you don't take any singular limit, then M with M doesn't commute. But if you take the limit L to infinity, then this vanishes like 1 over L squared. So this goes to 0. And this means that the M all commute with each other. So you get honest super translations. And for L going to infinity, this is indeed the BMS 3 algebra that was found earlier in flat space Einstein gravity. Okay, so this is what I said. So the contraction consists in taking the limit L to infinity, and you can think of L as the ADS radius. So that's literally the limit where the cosmology constant goes to 0. And as I said already, the M's then commute with each other. So those are the super translations. And for the concrete example of Einstein gravity, the values of the central charges are just the Brown-Renault central charges that we saw already in Alejandro's talk and others. So C is equal to C bar is 3L over 2G. So you see that the central charges themselves would diverge linearly in L as L goes to infinity. But because of this rescaling 1 over L, you get a finite result for Cm, it's 3 over G. And because the Virasoro central charge is the difference of the original ones, you get 0 for Cl. So these are indeed the central values that were found in the original analysis of flat space Einstein gravity. Okay, so this is BMS 3. Let me now come to the motivation for BMS 2. One motivation is just curiosity, because it's there. Well, maybe. We'll discuss this on the next slide. If it is there, it should be useful for toy models of flat space holography. It might be useful for near horizon holography, just because generic aspects of the horizon are that you have a null hypersurface. So you need one space and one time dimension, then some extra internal dimensions. So maybe some essential part of what happens near horizon is captured already by the two-dimensional part of it, which you usually depict in the Penrose diagram. And finally, one goal is to construct SYK-like models, but not in asymptotically anti-de Sitter space or nearly asymptotically anti-de Sitter space, but in asymptotically flat gravity. And here I've stolen a slide from Douglas Stanford's talks at Strings 2017, why SYK in ADS. So why the original SYK model is interesting. You may learn something about black holes, about chaos in the radial limit, about ADS2, about strange metals. And you can have similar motivations for studying flat limit of that. Okay, so what are the difficulties with BMS2? One is a generic aspect of two-dimensional gravity. Boundary charges are codimension 2 entities. Codimension 2 in 2 dimensions is structureless, so one could also say it's pointless, so it's just a point. So there's no angle dependence or anything that you can have in your charges. But you know, we learn to deal with this in ADS2. So maybe it's also sort of okay for BMS2. The other potential difficulty is that while it's very easy to get the ADS2 algebra from the ADS3 algebra, just take 1 chiral half. So basically you get rid of one Virasoro algebra and the remaining one is then the asymptotic symmetry algebra relevant for ADS2. The same cannot be true for a relation between BMS2, BMS3, because it's not clear what would mean to take a half of BMS3. Should it take half of the super translations and half of the super rotations, or just the super translations, or just the super rotations? So, and just the super rotations can't be true because that would be the ADS2 algebra. So it's not so clear how to go from BMS3 to BMS2. But okay, that's also okay. It just means we have no quick way of cheating towards BMS2. We have to make an honest intrinsic two-dimensional analysis and cannot deduce the result from 3 dimensions. Another issue is that, you know, you can have super rotations only in time directions. So in ADS3 or in flat space in 3 dimensions, you have still a celestial sphere. So you have diff S1, where the S1 refers to the celestial sphere. But, well, this point is related to the first one. In 2 dimension, there's no celestial sphere, there's just a celestial point. So you cannot rotate that point in any meaningful way. So the only way you can have some interesting things like diff S1 or diff of the line is if you do them in time direction. And that might be hard to interpret in the Lorentzian theory, but it is okay, at least in the Euclidean theory. And finally, super translations, well, can only be radial super translations because, again, there's no angle dependence. So it's impossible to have angle dependent translations in 2 dimensions. So to evade this difficulty, we need something like radial super translations. And okay, why not? I mean, if the associated charges with the symmetries are non-trivial, then they might be fine. So my general attitude is to ignore all these difficulties and rather than trying to prove some no-go result, just proceed and hope that it works. So this is inspired by a comment by Peter van Nieuwenhuizen, who once said that the task of theoretical physicists is to break no-go theorems. Okay, so let's move on to the kinematics. I want to define now the class of metrics that we're interested in. So those should be asymptotically Ricci flat metrics. In 2 dimensions, there's only one scalar invariant that you can construct out of the Riemann tensor. So it's the Ricci scalar. So we have to make sure that the Ricci scalar vanishes asymptotically. For convenience, and also because this is, you know, the same kind of gauge fixing you do in high dimensions in asymptotically flat space, we gauge fix to Eddington-Finkelstein coordinates. So we use retarded time u, some radial coordinate r, and the line element is of the form ds squared is minus 2 du dr, plus some function of u and r du squared. Now, it's not obvious that this is possible with proper gauge transformations. So this is a caveat that actually applies to any gauge fixing that you do when you make some asymptotic expansion. It also applies to Pfefferman-Graham expansions. So the Pfefferman-Graham theorem that tells you that you can always put, for instance, any asymptotically ADS3 metric into Pfefferman-Graham form, that's a true statement, but it's not evident that you can always achieve this by some proper gauge transformation. So if you want to address this issue, you should avoid any gauge fixing and try to find the most general class of boundary conditions that is compatible with asymptotic flatness. But here we are more modest. We're fine with gauge fixing to Eddington-Finkelstein coordinates and just look for boundary conditions in this restricted setup. There might be and will be generalizations of this, but already in this restricted setup, we find interesting structures. So let's focus on this. Okay, so the function k is not arbitrary. If we demand Ricci flatness, it's constrained to be a linear function in the radial coordinate. So, well, for some notational reasons, we have some factors too, but other than that, it's just some arbitrary function of u times a linear term in R plus a constant term in R times another arbitrary function of u. If those functions are constant, then we find a killing horizon. And in most of my talk, I'm going to assume constant P and T. So I'm not going to be very explicit. Sometimes results that I present are valid for arbitrary functions of U. And in some cases, for instance, when we do thermodynamics, we assume that these are constants. But to reduce clutter a little bit, I'm not giving the arguments U all the time. Okay, and our boundary conditions then demand that asymptotically, so for large values of R, the metric looks like this with this function of K, potentially plus subleading terms. And these functions can vary arbitrarily. So they're not fixed, they're arbitrary fluctuating functions. If you want, you can call them state-dependent functions. So whatever the gravity theory is going to be, we require the following boundary conditions for the metric: minus 2 du dr, plus some order r term, plus a order 1 term, plus a small o of 1, so terms that vanish as r goes to infinity, times the u squared. This is the class of metrics that defines for us asymptotically flat boundary conditions. Okay, so now that we've fixed the boundary conditions, let's determine what are the asymptotic killing vectors that preserve this class of metrics. And that's a straightforward exercise. So we have written down again the metric, and you find that Lie variations of this metric along vector fields of this form preserve this form of the metric. So you have two arbitrary functions parameterizing this asymptotic killing vectors. So that means they're again infinitely many. You have epsilon of u, which generates the analog of super rotations, but in u direction. And then we have this radial super translation. So indeed, we have translations into r direction, but with a coefficient that depends on u. So it's an arbitrary function of u. And for consistency, you also need this epsilon prime times r term. Prime means with respect to u. But this is not an independent function. So there are two independent functions parameterizing all the asymptotic killing vectors. Okay. Now, when you act with these asymptotic killing vectors on these metrics, you get again metrics of this form, but with different functions p and t. And you can check how this function transform infinitesimally, and what you find is displayed in this equation. So p transforms like a U1 current, or like a spin 1 field. So you have epsilon p prime plus epsilon prime p plus some anomalous term. And t transforms like a Virasoro stress tensor. You have epsilon t prime plus 2 epsilon prime t, but there's no Virasoro anomalous term. So there's no epsilon triple prime term. Instead, there are these funny looking anomalous terms, eta prime minus eta p. So this looks indeed somewhat promising. P transforms like U1 current and T like a Virasoro generator with some central terms. So let's now try to proceed. First, let's consider the core part of this talk, the BMS2 algebra. So this is just the Lie bracket algebra of asymptotic killing vectors. So if you take the Lie bracket of two killing vectors of the previous form, you get again a killing vector of that form with this combination of parameter functions. And to bring this into more familiar form, you can introduce Laurent modes, or if you go to Euclidean signature and you compactify, you can also introduce Fourier modes, and you get the same algebra. So L with L just gives a width algebra. So this is subalgebra. L with M gives some mixed term that, well, looks a bit like a sign mistake because you have minus n minus m. So if there was plus n minus m, this would just be BMS3, but this minus is there, so it differs from BMS3. And m with m vanishes, so that shows again that m, the generators of super translations, indeed also algebraically have the property of super translation, so they commute with each other. The novel feature of this algebra as compared to BMS3 is that the super translations of spin 0. And I'm going to call this algebra BMS2. And as we'll see later, this will have non-trivial central extensions in a specific gravity model. just on general grounds, you can check what kind of cocycles you can put there, and then you find this algebra can have several non-trivial center extensions. But in the gravity model that we consider, only one of them is going to be switched on. Okay, before moving on to dynamics, let me discuss some interesting global aspects. So let me redefine the function that generates the super translations, eta, as sigma prime. So this is very harmless looking. We also redefine the corresponding generators. I call them now Jn, and these are just the Laurent mode with respect to this new parameter function sigma. And what you see is an algebra that is probably familiar to many of you. So this is just a centerless warped conformal algebra, or with algebra with a U1 current algebra, but there's no level, there's no Virasoro central charge, and there's no twist term in this commutator here. So in this case, J is a spin 1 current. So what happened here? Previously we had a spin 0 current. Now we have a spin 1 current, which again generates super translations. So all the J's commute with each other. So you can see that because of this prime here, you get a similar relation between the super translation generators. So the relation between new super translation generators and old ones is a factor of n. So this is a baby version of a twisted Chugavara construction. There's no bilinear term, there's just a twist term. So J is essentially the derivative of M. But this works only if n is not equal to 0. So this is almost a change of basis up to the 0 modes. So in particular, J0 is not, is mapped to 0 in this relation, and nothing maps to M0. And as we'll see later, M0 is interpretable as a winding mode of the Maxwell field. So when you have a relation like this, you have to make up your mind. If you introduce Fourier modes, either eta has no 0 mode, because it's given by the derivative of something, or sigma is not a periodic function, but only a quasi-periodic. So depending on which perspective you take, you either get naturally the BMS2 basis or this warped width algebra basis. Now, in my talk, I'm going to dismiss the winding mode and focus on the warped width algebra. But up to this issue of 0 modes, it's equivalent to the BMS2 algebra.
Daniel?
Yes.
Hey, quick question. If you do have central charges and levels, how does that relation get modified? Is there such a relation?
This one?
Yes, that one.
It's not going to get modified in our case. It's the same relation. Well, there might be, no, it's the same relation. It's the same relation.
Oh, you don't get like a Kronecker delta, like proportional to this?
No, because the Kronecker delta that you get is to adjust the mapping of the 0 mode, but the 0 mode is not mapped here anyway. So the 0 mode is not part of this change of basis. So it's something you have to deal with separately.
Okay, but even if you have central charges, then that's basically
even if you have central charge, even if central charges, it's the same kind of map.
Okay.
Yes.
Okay. Thanks.
But note that we're not going to have a U1 level, so there's not going to be a central charge here. So we always have honest super translations. So if you want to have super translations also at the quantum level, it's actually important that you don't get the central extension in the J's or in the M's. And this is indeed what you find. If you would get a central extension here, I wouldn't call this BMS. Then I would call it warped conformal algebra. So it's quite important that this guy here doesn't get central extended. Those two, the first two, can get centrally extended. And we will see that one of them indeed will get centrally extended.
Okay, okay, thanks.
Sure. Yeah, okay. I guess this is needless to say, but if there are any questions, then just interrupt me. And if anyone has microphone problems, you can also write in the chat. I have the chat window open and can read stuff there. Okay, good. So this now finishes my definition of what I mean by BMS2 and the boundary conditions for asymptotically flat metrics in 2 dimensions. And now the next step is to find an actual theory where you can impose these boundary conditions and where you find a canonical realization of these asymptotic symmetries, possibly with some central extension. So the class of theories that we're going to consider are Einstein-Dilaton-Maxwell theories. So if you've never seen Dilaton gravity in 2 dimensions, I can refer you to our review from 2002. And some general aspects of boundary conditions and boundary terms in Einstein-Dilaton-Maxwell theory you can see in this work with my former student Jakob Salzer. Okay, so this is how the second order action looks like for Einstein-Dilaton-Maxwell gravity. So let's unpackage this a little bit. So I call it Dilaton X. It's a scalar field, and I define it by its coupling to curvature. So there are different conventions that are possible. Usually people write either, well, the way I'm writing it here, x times r, or sometimes there's a phi squared times r instead, or a e to the minus 2 phi times r. But it's clear that by redefining the scalar field, you can always bring it into that form. Okay, so then there's a kinetic term, and that kinetic term can contain an arbitrary coupling function, u of x. So as opposed to Einstein gravity in 3 dimensions, where you have no free functions and the only free parameters are the cosmology constant and the Newton constant, here you actually have an infinite amount of choices for model building, namely an arbitrary function u of x and another arbitrary function v of x. So v of x is the self-interaction potential, and you need this to be non-zero to get non-trivial geometries. Okay, so this is the bulk action. G2 is just the 2-dimensional Newton constant. M is some 2-dimensional manifold, either with Lorentzian or Euclidean signature. And in general, it will have some boundary. So there are also boundary terms contributing to the action. There's the usual Gibbons-Hawking-York-like boundary term. So extrinsic curvature, and like the bulk term, it's multiplied by the dilaton. So this guarantees for you a Dirichlet boundary value problem for the metric, but then you also need a holographic counter term to get a well-defined variation principle. And that holographic counter term is the superpotential. So it's some bizarre looking combination of the original potentials U and V. And there's some fine print that I didn't intend to go into unless someone asks me about this.
Daniel?
Yes.
But u of x, you can remove it by a conformal transformation.
That is true. So you can go to different Weil frame. So you can do a Weil rescaling of the metric. Yeah. And then you get a conformally related model. And that, sometimes is useful, sometimes it may simplify things. But you have to be a bit careful because some especially if you're interested at some stage in the quantum theory, because some quantum properties depend on the Weil frame that you choose, because the Weil rescaling that you do is singular in the asymptotic region and also at the singularity. So it's not necessarily as harmless as it might look. Locally, it's totally fine to do this, but locally the model is essentially trivial. So we are eventually interested also in global properties, because like in 3D gravity, if you dismiss global properties, then you're not left with much, right? Because locally, both 3D gravity and 2D gravity are trivial. So that's why I usually insist on keeping this and don't remove this. But you're absolutely right that locally you can always remove this by a dilaton-dependent Weil rescaling.
No, but okay, yeah, I agree. Yeah, okay, thanks.
Okay, so yeah, so this holographic counter term guarantees that the first variation of the action vanishes for all variations that preserve most of the boundary conditions, but actually not the ones that are of relevance for SYK. And an interesting option is to couple dilaton gravity to matter, and I have specified the matter action here explicitly. So for the matter action, we're using Maxwell's theory. So we have an abelian connection A, F is the field strength of it, and small f of x is some coupling function. So then we have a third coupling function which we can tune to do model building. And the nice thing about Maxwell's theory in 2 dimensions is that it doesn't spoil the topological nature of that model. So that model has 0 local degrees of freedom, 0 propagating physical degrees of freedom, and the same remains true when you include a Maxwell field. So that's different from 3 dimensions where you would add degrees of freedom if you added a Maxwell field. So here you can do this basically for free. And we're going to need a Maxwell field, so that's why I'm introducing it here. Okay, so don't worry, I'm not going through this whole table here. This is just to show that, well, of this infinitely many choices for U and V, a finite but relatively large number has appeared in the literature, and this list is by no means exhaustive. There's some color coding, so this orange or brown entries are asymptotically de Sitter or anti-de Sitter. The green ones are asymptotically flat, so we're interested in the green ones. And the blue ones have additionally the Wheeler property. By Wheeler property, I mean the property that, you know, matter tells spacetime how to curve. So spacetime is only curved if there is actually matter. This is not true for generic dilaton gravity. Generic dilaton gravity models will lead to metrics that have curvature even in the absence of matter, just because the dilaton, even though it has no local degree of freedom, still is something like matter. But there are some exceptions. One is Liouville gravity, which obeys this Wheeler property, and the other is the CGHS model. And you see that the CGHS model, so modeled by Cullen, Giddings, Harvey, and Strominger, both has the property that it's asymptotically flat, it has this nice Wheeler property, and it has the desirable option that Alejandro pointed out, namely that the kinetic potential vanishes. So this is the main option on which I want to focus, because it's the simplest model that has the required features of asymptotic flatness. Okay, so how did we analyze 2-dimensional dilaton gravity? Well, if you're familiar with 3D gravity, then you probably know that it's very convenient often to use the Chern-Simons formulation of 3D gravity, because that gives you a gauge theoretic handle on Einstein gravity. And we have many techniques available for gauge theories, particularly of Chern-Simons type. So it's fair to ask if there's something similar in 2 dimensions, and the answer is yes. It's the 2-dimensional version of Chern-Simons formulation is the Poisson-Sigma model formulation. So Poisson-Sigma models were introduced in the early 90s by Ikeda and by Schaller and Strobel, also at TU Wien. And the main difference to Chern-Simons theories is that these Poisson-Sigma models are nonlinear gauge theories in general. And they're rigid in a very precise sense. So I don't want to get too technical, but there is the notion of consistent deformation of gauge theories introduced or defined precisely by Barnich and Denot in the 90s. And you can show that Poisson-Sigma models are rigid in the sense that the most general consistent deformation of a Poisson-Sigma model is another Poisson-Sigma model. But for our purposes, we don't have to go into this Poisson-Sigma model formulation. For our purposes, it turns out that a linear gauge theory version of this Poisson-Sigma model is sufficient. So we get linear but non-abelian gauge theory. So in that sense, it's even more closely related to Chern-Simons theory. So the non-abelian BF action, that is the analog of the Chern-Simons formulation of 3D gravity, is written here. So it's called BF action because the Lagrangian is BF. B is some scalar field, and F is the non-abelian field strength associated with some connection A. Kappa is some coupling constant similar to the Chern-Simons level, and these brackets here denote some invariant bilinear form on this gauge algebra. So for an interpretation of this BF action as a 2D gravity model with a Maxwell field, we choose the connection 1 form as follows. So we dualize the spin connection. That's more or less similar to what people do in 3 dimensions. There you also dualize the spin connection, but to something that still has an index. In 2 dimensions, when you dualize the spin connection, you don't have an index. So just have a 1 form omega multiplied by some generator, which will be the Lorentz generator. Then you have the Zweibein multiplied by some generator, which is translation generator. And then you have the Maxwell connection multiplied by some additional generator that we call Sept. And the scalar field can also be expanded in the spaces here. So it's x times z plus some xa, epsilon ab, pb. Epsilon is just the Levi-Civita symbol, and these flat indices are raised and lowered with the Minkowski metric in 2 dimensions, and then y times j. So x, xa, and y are scalar fields. X will be the dilaton field. That's why we choose the same letter. And xa and y don't appear in the second order formulation. They are auxiliary fields from the second order viewpoint. Okay, so at this stage, we still need to choose some gauge algebra and the bilinear form. So what I've said so far is, somewhat general. It applies to any non-abelian BF theory that has a gravity interpretation. There are not so many of them, but there are different ones. For instance, Chakif-Teitelbaum model is one example. And here we're not interested in Chakif-Teitelbaum, so I need to specify what we choose to not get Chakif-Teitelbaum. Instead, we want the Kangemi-Chakif version of the CJJS model. And for this, it turns out that we need to choose the Maxwell algebra. So the Maxwell algebra is defined here. It's a centrally extended Poincare algebra in 2 dimensions. So the translation generators commute up to the central term here. And the translation and boost generator, well, they don't commute in the usual way. So they give a translation generator. And the bilinear form is non-degenerate. Between the translations, it gives the Minkowski metric, and between J and Z, it gives -1. And if you insert these definitions into this BF action and integrate out these auxiliary fields XA and the spin connection, then you get this action here. And this action is essentially the CJJS model. So this action still functionally depends on the dilaton, on this auxiliary field Y, on the metric, and on the Maxwell connection. And it's straightforward to derive the equations of motion. And the first one, when you vary the dilaton, establishes that all solutions are Ricci flat, which is precisely what we want for flat space, asymptotically flat space. Varying the gauge connection, varying Y, the auxiliary field Y, establishes that the dual field strength is 1. So there's some electric field. Then varying the metric gives some second order equations for the dilaton field, and varying the gauge connection just establishes that Y on shell is some constant. And when you integrate out the gauge connection, you get back the CJJS action, which just consists of XR minus some constant. Okay, so this means that the metrics are indeed Ricci flat, so they fall into the class of metrics that I've discussed before. So all we have to do is to translate our boundary conditions into the BF formulation. And again, if you're familiar with 3-dimensional gravity, what I'm displaying here is not going to surprise you. So there's an ansatz that works nicely in 3 dimensions, and the similar ansatz worked nicely for the Chakif-Teitelbaum model, for the BF formulation of the Chakif-Teitelbaum model. So we use the same type of ansatz. So what we do is we split the bulk connection into a boundary connection, small a, that depends only on the boundary coordinate u, and a group element b that is state independent and depends only on the radial coordinate. You have to work a little bit to find out that you need to choose b to be the exponential of minus r times p plus to recover Eddington-Finkelstein gauge, but it's not hard to show this. And we use a similar ansatz for the scalar field. So also the scalar field big B is b to the -1 small x times b, and small x again depends on functions that only depend on the boundary coordinate u. And well, these functions t and p that appeared in the metric also appear in the connection. So you see this resembles a bit well, highest weight gauge connection in 3D gravity. And T and P are again arbitrary functions that are allowed to vary. So this defines our boundary conditions in this BF formulation. So this indeed yields the metric that I've shown to you before. The dilaton is going to be a linear dilaton. So X is some function of U times R plus another function of U. But note that this function is allowed to fluctuate. So it's different from the linear dilaton vacuum that people have considered until about 2013. Until then, this leading order term was always fixed. But for purposes of SYK JT correspondence and its flat space generalization, you need to require that this is allowed to fluctuate to leading order. So this is a technical detail, but it's a very important one, and that's why I mention it. Okay, and for the Maxwell field, you just get A is R times du. So there's no state dependence here. You just have the Coulomb potential in two dimensions. So you know, in two dimensional Coulomb potential is a confining potential. It's just linear in R, and that's what it is. Okay, so we indeed get the BMS2 asymptotic symmetries just because we have the same metric as before. The dilaton field is preserved by this BMS2 symmetries because these functions are allowed to vary. So all these BMS2 generators preserve this asymptotic form of the dilaton. But it's non-trivial or non-obvious that the Maxwell field is preserved by these BMS2 transformations. And in general, it isn't. But you can compensate the violation of this by a U1 gauge transformation. So if you combine a diffeo and the gauge transformation, then the Maxwell field transforms as follows, where this is again a reminder of how the asymptotic killing vectors look like. And it turns out that if you choose this U1 gauge transformation sigma in this way, so that eta is equal to sigma prime, where eta is the function that generated the super translations, then this Maxwell field is indeed preserved by these BMS transformations combined with the gauge truffles. So we see that what I mentioned on this slide when I talked about global issues is indeed important. We have to make up our mind if we allow a zero mode for eta, or if we demand that sigma is single valued, but you can't have both. If sigma is single valued, meaning that it's a periodic function, if we compactify, that means that eta has no zero mode. Conversely, if eta has a zero mode, then sigma cannot be single valued, so then we need some winding modes. And I mentioned already in this talk, I'm going to dismiss winding modes, but for slight generalizations and applications, it could be important to consider these winding modes. Okay, so we're going to focus on the case where this Wilson loop is gauge invariant and the winding modes, and then the asymptotic symmetry algebra is a central extended version of the warped width algebra. Okay, so okay, I have 12 more minutes. That's fine. So what we are after as a main result is the flat space analog of the Schwarzian action. So if you're familiar a little bit with the SYK JT story, then you must have heard about the Schwarzian action, which arises as an effective action, as an effective boundary action that governs the low temperature modes at large n. And we want to, derive something similar on the gravity side in this flat space model. So the way we proceed is inspired by the way we derive this for the Chekif-Teitelbaum model. So for Chekif-Teitelbaum, we use this BF formulation. Here we use the same technique. So what we require is that the first variation of the BF action vanishes once we included appropriate boundary terms. If you just take the plain vanilla BF action without boundary terms, you find a bulk term that just gives you the equation of motion, but then you find this boundary piece. And this boundary piece is in general non-zero because delta AT is non-zero. T is now the Euclidean version of time. And X, well, the bilinear form between X and delta AT is in general non-zero. So this term is non-zero, so you don't have a well-defined variational principle. So the goal is to achieve a well-defined variational principle by canceling this boundary term. And we do this by adding a boundary action, which I call TW for twisted warped, for reasons that will become clear in a bit. And as I said, we just follow the Chakif-Teitelbaum story in the BF formulation. So the Schwarzian action was not originally derived in this BF formulation, so it was known before that you have the Schwarzian action just in the metric formulation. But we found it useful to rederive this in the BF formulation because that allows certain generalizations more easily, for instance, generalizations to higher spin that we considered here, and also generalization to flat space considered in the present talk. Okay, here's just some notation. I defined some functions f and g in terms of the functions that appeared in the dilaton. So they were called x0 and x1, and up to some irrelevant factors or signs. 1 over x1 is the time derivative of f, and x0 over x1 is the time derivative of g. And then we do a similar construction as for the SYK model. So we introduce a variable tau, which is just this function f of t, and a function h of tau, which is the inverse function f to the minus 1 of tau. And we compactify tau with some period beta, which is then interpreted as the inverse temperature. And prime now means derivative with respect to tau. So with all these definitions in place, this is the analog of the Schwarzian action. So if I had done the same manipulations for the Chakif-Teitelbaum model, what you would have seen here would have been the Schwarzian action, but now I'm doing this for the Kangemi-Chakif version of CGHS, and we get instead this twisted warped action. So this twisted warped action depends functionally on two fields, H and G, and it's an integral over Euclidean time tau with some period beta. You have the state-dependent quantities T and P appearing in the action, and you have some kinetic term and some higher derivative terms that, well, in this case, only second derivative term that appears non-polynomially. So this is what we call twisted warped action. Why is it called twisted warped action? Well, I'm not going to bother with technical details, but let me explain why we call it this way. So this is the flat space analog of the Schwarzian action. And what is the Schwarzian action? Well, from a geometric viewpoint, the Schwarzian action is the group action for Virasoro coadjoint orbits. So this goes back all the way to Witten and Alexeyev Shatashvili in the 80s. So the twisted warped action that we have here is something analogous to the Schwarzian action. It's also a group action, but not the group action for Virasoro coadjoint orbits, but rather the group action for twisted warped coadjoint orbits. So what are twisted warped coadjoint orbits? Well, these are coadjoint orbits associated with the twisted warped algebra, and it is defined here. So the twisted warped algebra is the algebra that you've seen already. So it's just the width algebra with some centerless U1 current, some U1 current with no level. But now there's a central extension. And you see there's no central extension in this term. So these are still super translations. There's also no Virasoro central charge, but there is a twist term. So this is a term that usually you can get rid of by doing a twisted Chogovara construction, but this does not work if the U1 level vanishes. So this central term here is genuine. It's a non-trivial cocycle. You cannot get rid of it. And if you take this algebra and ask the question, what is the group action associated with it, you find this result. Okay, you can check that under the asymptotic symmetries, H and G are boundary scalars under diffeos, and G transforms like a phase under U1 transformation. So G has the interpretation as a phase field. So for people who are familiar with complex SYK, this should ring a bell, because also there you have a field H that and a field G that both are boundary scalars under diffeos, and a field G that is a phase field under U1 transformation. So maybe there's some, similarity between complex SYK and this twisted warp action. And what I want to show in the remaining minutes is that there's not just a similarity, there's a precise limit from complex SYK to this twisted warp action. Okay, So maybe I'll skip the Hamiltonian formulation because all I want to mention here is that the Schwarz and Hamiltonian action and the twisted warped Hamiltonian action look similar, and that the on-shell action is finite and determined by some quantity G1 that is related to the quasi-periodicity of this canonically variable Q2. So it's basically related to the quasi-periodicity of this function H. Before discussing the limit, I need to mention thermodynamical properties of this CGHS model. So in particular, the entropy and the specific heat. If we assume that this quantity G1 is independent from temperature, then it turns out that the entropy is just given by minus the on-shell action. So it's just given by this quantity G1. And if you use the equations of motion, you find that G1 is nothing but the dilaton evaluated at the horizon. So not surprisingly, you recover the well-known formula that entropy is given by the dilaton evaluated at the horizon times times the coupling constant. So this is a standard result that you can derive using, for instance, Wald's entropy. Now, we can derive this assumption that G1 is independent from temperature in a sort of usual way from regularity conditions, and the regularity condition gives a relation between P and temperature, but T is arbitrary. So on-shell P is just this quantity Y, which is the U1 charge, while T is the mass. So that means temperature and mass are independent from each other. So this is a rather unusual property, which you don't usually have in black holes. And one peculiar consequence of this is that the inverse specific heat vanishes. This is in fact a well-known property of CGHS. So if you calculate the inverse specific heat defined here, the T by ds, you find this is 0. Now, this is useful to remember when we try to find a scaling limit from complex SYK, because the specific heat enters there essentially as a coupling constant. So having specific heat going, inverse specific heat going to 0 means that the specific heat has to go to infinity. So we need to take a specific singular limit of complex SYK. Okay, so here it is. This is the complex SYK action. So this is the effective action governing collective low temperature modes of the complex SYK. So instead of Majorana fermions, you have complex fermions. You can see this, for instance, in this recent paper by Gu, Kitaev, Sachdev, and Tarnopolsky, but there's also earlier work where this appeared. So let me define all these quantities. So these braces are the usual Schwarzian derivative. So without this first term, this would just be the usual SYK effective action. N is the number of complex fermions, which is assumed to be large, so that we have a gravity limit. N times gamma is the specific heat at fixed charge. So we see that we have to take the limit where this is going to infinity. K is the zero temperature compressibility. That's the factor in front of this first part of the action. Epsilon is a spectral symmetry parameter. H of tau is the time reparameterization field, which is quasi-periodic. So this is the field you have also in the SYK model. And G of tau is the phase field, which is periodic in the absence of winding. So for our purposes, you can assume it's periodic. Now, according to our thermodynamics, we expect that we should take the limit n times gamma to infinity, infinite specific heat. And it turns out, if you analyze the model, you need additionally the limit where k goes to 0. So with vanishing zero temperature compressibility. But you have to take this limit in such a way that their product is finite. So gamma times k times some suitable exponent of n is kept finite. And in this limit, you can show in a few lines of calculation that indeed this complex SYK action is equivalent to this twisted warped action. So there's a concrete singular limit where you can obtain this limit. Maybe let me just summarize what happens on this slide. You can derive the same statement at the level of symmetries. So if you start with the twisted warped Virasoro algebra, so the warped width algebra with all co-cycles switched on, Virasoro central charge, twist, and level. Then complex SYK corresponds to the choice where the twist is 0 and Virasoro and U1 level are non-zero. And our model is complementary. It has Virasoro charge equal to 0, U1 level equal to 0, but the twists are not 0. And you can map first twisted warped Virasoro to warped Virasoro in this way, and then take the limit where k hat goes to 0 and c to infinity, keeping fixed this ratio, and then you go over to the twisted warped. So the same limit that worked at the level of the action also works for the symmetry algebras. Okay, so I think I'm basically essentially out of time, so let me conclude here. For more details, just look at the paper. So this is just the main bullet point. We looked at CHS a la Kangemi-Chakif as a bulk model for flat space holography. So this is the Einstein-Maxwell-Dilaton action that we used. We imposed asymptotically flat boundary conditions that yield BMS2 symmetries. And the boundary action, the analog of the Schwarzian action, is this twisted warped action with the phase field G and this diffeo field or requantization field H. This action follows as a singular limit from complex SYK in the limit of large specific heat and small compressibility. And also the asymptotic symmetries follow from a singular limit of warped Virasoro. So the main conclusion here is this could be a useful toy model for flat space holography. And let me just put these points as an outlook. There's more you could add, like this islands discussion by Hartmann, Shagulin, and Strominger, and other stuff. Okay, so let me stop here and thank you for your attention.
All right, let's thank the speaker. Questions, comments?
Maybe I'll ask a question.
Sure.
Just, yeah, thanks. It's a very nice talk. I had yeah, the case where you have the warped, this complex SYK where you have the k hat. What is an example? I guess there are examples where this k hat was computed in the gravity side, right? Do you know who, perhaps? They're like a 2D theory of gravity that gives you a non-trivial k hat.
That's a good question. Actually, I don't know.
Really?
So it would not be a pure gravity model. It would be a Einstein-Dilaton Maxwell model.
Yeah.
But yeah. I'm not, well, let's see. I guess a simple candidate would just be charged Chakif-Teitelbaum model. Yeah, I actually don't remember if that was done. I mean, charged Chakif-Teitelbaum was considered for sure.
Right.
Yeah, I don't remember if a concrete gravity model was actually studied where this U1 level is switched on.
Yeah, as I said, usually the examples that at least I have looked at, they have that k hat is 0. So I was just curious if you knew of someone that had an example where that k hat was not 0.
I mean, yeah, unfortunately, I was a bit decoupled the past semester, so it might be that there was a work in the past 6 months and I've missed it. In the original, or in the paper by Gu, Kitaev, Sachdev, and so on, and Tanopolsky, I think they also discussed something about the bulk picture of the SYK model. I mean,
I see. Yeah, I'm just.
You can look at the paper, but just looking at it quickly, I don't actually see a bulk action. So, but I mean, the guess is it should be just charged SYK, charged Chakif-Teitelbaum 1. So Chakif-Teitelbaum with a U1 charge. The problem is just that, so the way that you naturally would get a U1 level is if you have additional gauge symmetries, namely the U1 gauge symmetries that become asymptotic symmetries, and that gives you a U1 level, right? So that's generally how you can get it from a Maxwell field. Here, the reason why this doesn't happen is because the gauge symmetry that we had was not independent from the bulk diffuse. So the U1 gauge symmetry was completely determined by the bulk diffuse, since the Maxwell field had no state-dependent function in it. So actually, sorry, I know the answer. It's quite easy. If you just take a non-abelian BF theory where you have SL2 plus U1, then you get for suitable boundary conditions, then you get K hat not equal to 0, and also the Virasoro central charge not equal to 0, but the twist term would be 0 then. So that is possible. Yeah, sorry. It's actually straightforward.
Okay, no, this is okay. I've looked at some of these 2D models with a Maxwell field, but I was getting that the level was 0, although the central charge wasn't true.
I will send you a link. I think.
Okay.
I think the solution is actually in one of my papers now that I think of it. So
Okay.
yeah.
You're the right person to ask that, I'm pretty sure. Okay.
Yeah, but apparently I'm getting older, so I'm forgetting stuff. So no, I'll send you the paper. I think
Okay.
I know know where it is, and I can point you concretely to an example where the U1 level is non-zero.
Okay, great. Thank you.
Sure.
Okay. Any other questions? Okay, let's thank Daniel again.
Thanks.
Thanks, Daniel. So we'll begin again at 3:15 Lisbon time. So that's in 8 minutes, primarily. Okay, till then.